All right, guys, so what we're doing today is we're continuing on with these statements. So yesterday we talked about conditional, inverse, converse, kind of these statements. And what we're talking about today is biconditional. A biconditional statement is a statement that contains if and only if and is true both ways. One implies the other. Both statements are true. When you write a conditional statement, when a conditional statement and its converse are both true, you can write them as a biconditional statement. A biconditional statement is a phrase that contains if and only if. So we don't have if this, then that. It's not an if then. It's our if and only if. So we have two statements combined with if and only if. So first off, we're going to start writing some phrases. So this here they gave us the definition. If two lines intersect to form a right angle, then they are perpendicular lines. So this here is true both ways. So no matter how we write it, it's going to be true. So what we can do is we can rewrite it as a biconditional statement. So we'll have two lines intersect to form a right angle. So we took out the if and then. So let me get my highlighter. So the if here and the then here, we take those out. We get rid of those. And what we're going to do is we replace it. So we have the first statement, two lines intersect to form a right angle, if and only if they are perpendicular lines. And that's it. So we replace the if and then with if and only if. Now, you might be wondering if we could say if we did it the other way, they are perpendicular lines. Well, two lines are perpendicular if and only if they intersect to form a right angle. Now, I had to change it a little bit. I had to change the statement a little bit because it was kind of wordy. The wording of it was a little wrong. They are perpendicular lines if and only if they intersect, if and only if two lines intersect to form a right angle. So I kind of reworded it a little bit. Two lines are perpendicular if and only if they intersect to form a right angle. They go both ways. So you can either pick the one we did at the start, so this one here as your if and only if biconditional statement, or this one here. They are both correct. We can use either one. Now let's look at this one here. If an angle is a right angle, then it measures 90 degrees. Well, if the angle is 90 degrees, then it's a right angle. One implies the other. They are both true because a right angle is 90 degrees, and 90 degrees is a right angle. One implies the other. So what that means is I can change it. I can drop the if and then. So we don't need this if and we don't need this then because we can rewrite this as a biconditional statement. And we can say an angle is a right angle if and only if its measure is 90 degrees. If and only if its measure is 90 degrees. And that's it. That's all we have to do for this here. We just change it from if then to if and only if because both statements work. If two line segments have the same length, then they are congruent. Well, if two line segments are congruent segments, then they have the same length. So again, this is another biconditional statement. So what we can do is we can drop the if and then and say two line segments have the same length if and only if they are congruent segments. And that's it. That's all we have to do for this here. So if it's true both ways, then it works. Rewrite the statement as a single biconditional statement. If you can run for president, then you're 35 years old. If you're at least 35 years old, then you can run for president. Well, that's true both ways, yes? Because If you can run for president, it means you're 35, at least 35. If you're at least 35, it means you can run for president. So even though we have two statements here, we have this statement here, and then we have this statement here. Are they saying anything different? Well, no, they're saying the exact same thing. So I can write them as one statement. You can run for president if and only if you are at least 35 years old. And that's it. That is our biconditional statement. Now, some of you might, some of you might be wondering, well, could I have said you are at least 35 years old if and only if you can run for president? Yes, but it just doesn't sound right. I would go with the other one. You can run for president if and only if you're 35 years old. I mean, it works both ways because there's nothing wrong with saying it the other way. It just doesn't sound right. So we have this here. You can run for president if and only if you're at least 35 years old, because this is a biconditional statement. If Mary's in the theater, then she will be in the fall play. If Mary's in the fall play, then she will be taking theater classes. I read that first sentence wrong. I just realized that. If Mary's in theater classes, if Mary's in theater class, then she will be in the fall play. If Mary's in the fall play, then she must be taking theater classes. So both of these are true. So all we've got to do is pick one. So I can say Mary is in theater class if and only if she will be in the fall play. We could also say Mary is in the fall play if and only if she is taking theater class. Now I changed it a little bit there because the wording would have probably been a little funky. If and only if she must be taking theater class, she is taking theater class. But that's it. We're just rewriting as if and only if. Now we don't have to have both of them. We just need one of them. We just needed one of those two statements. Truth tables. Truth tables. So we have these here, these truth table values. And this is going to be a little bit weird for some of y'all because the truth table, so P is the hypothesis, Q is the conclusion. Well, if the hypothesis is true and the conclusion is true, then P implies Q is true. Okay, that makes sense. If P is the hypothesis and Q is the conclusion, if our hypothesis is true and our conclusion is false, it means the statement's false. Now, the other two cases are kind of, if the hypothesis is false, then the conclusion is true and the hypothesis is false. Well, if the hypothesis is false, well, kind of what do you guys guess? Probably you're saying, well, the whole thing is false, right? Well, no, the whole thing is true. If the hypothesis is wrong, the whole thing is true no matter what, because there's no way to prove it. It just ends up being true. The whole statement's true. So that's kind of a weird case for it. So when we try to prove something, we always want to assume and make it so that the hypothesis is true so that we can prove it. Because if the hypothesis is true, then we can actually determine whether it's true or false. And we only need one case for it not to be. Now we're going to look at this here. So our converse. So we have these here. So these truth table values are still holding up. So the conditional statement is what we just did on the first one. Now the converse, if you notice, Q implies P. So we flipped it. Here P implies Q, Q implies P. So if Q is true and P is true, well, the whole thing would be true. Since Q is false, our hypothesis is false. It means the whole thing is true. False and false down here, so the whole thing is true. And then our middle one, true implies false, is true, true, false, true. So we have this here. Now our inverse. Now inverse is not P implies not Q. So what I did is we set up P, we set up Q. So P not P. So the opposite of true is false. The opposite of true is false. The opposite of false is true, so we have those there. So these line up with not these. So that's where we get those there. Now the other one are these here. So these are going to be the opposite. So true, not true is false. False, the opposite is true. The opposite of true is false. The opposite of false is true. So we get these here. Now what we're looking at mainly is going to be this box here for the inverse. So we look at the inverse, we're only really looking at these here. So our first one is not P implies not Q. Well, false implies false, as we said earlier, is going to be true. False implies true is going to be true. Because again, whenever the hypothesis is false, the whole thing is true. True implies true is true, and true implies false would be false. We have this here. And lastly, our contrapositive. So we have our other statements, and they flipped them. This time I flipped them, or kind of the book did, so that we have it going just right to left. False implies false would be false, or true. False, false is true, because again, if the hypothesis is false, the whole thing is true. So here, this one here, so false implies true would also be true. True implies false would be false, and true implies true is true. So we kind of have these four. And we're not going to worry too much about these other tables, but one thing I want to draw attention to is that the conditional statement, like this, and the contrapositive were told to us to be the same. Well, let's look at the overall truth table values. So true, false, true, true. True, false, true, true. These are the same. So that's when we talked about yesterday or the other day, that the conditional statement and contrapositive will always have the same values. No matter what the statements are, they will be the same. So if it worked out that the contrapositive is false, the conditional will also be false. If the contrapositive is true, the conditional statement will be true. Now if we look at the inverse, true, true, false, true. And the converse, true, true, false, true. These line up as well. So the converse and the conditional, the inverse will have the same value. The contrapositive and the conditional will have the same value. So that's all we're going to cover on this here. We're not going to worry about the other truth tables, but we have these here. So the main thing, so at this point here, the video is done. We're done with this one here with 2.12. So after you guys finish this video, go on and work on the assignment for 2.12.